This week's lesson is based on the properties of water, which is a truly amazing molecule. Let's take a look. Water is the molecule that supports all of life. It's the biological medium on Earth, which means that all living organisms require water. Cells are about 70 to 95% water, and water is the main reason that Earth is habitable. Let's take a look at some of its characteristics that make it this amazing substance. First, let's talk about its structure. Water is a polar molecule. Polarity is what allows water molecules to form hydrogen bonds with each other. I have an animation that I'd like to show you with some narration that describes polarity and how that affects how water relates to other things in the world. Let's take a look here.
Life is based on water, primarily because of water's solvent properties. Understanding this and the other properties that make water so important means understanding water's molecular structure. Any molecule can be represented in several ways, each having particular advantages. Molecular formulas, for example, are compact and indicate the number and identity of atoms in the molecule. Structural formulas show the bonds between atoms. Ball and stick models take up more space than structural formulas, but include information about bond geometry. Space-filling models are not as easy to read as ball and stick models, but they depict the spatial relationships between atoms more accurately. Water is a solvent for many of the molecules in living organisms, primarily because it's a polar molecule. The oxygen atom in the water molecule has a high electronegativity. This means that electrons shared by the hydrogen and oxygen atoms are more attracted to the oxygen than to the hydrogen. This unequal attraction of electrons generates partial electric charges within the water molecule. The oxygen atom has a partial negative charge, and the hydrogen atoms have a partial positive charge. Therefore, a water molecule as a whole has positive and negative ends. The molecule is polar. When two liquid water molecules approach each other, the partially negative oxygen atom of one water molecule is attracted to the partially positive hydrogen atom of the other water molecule. Hydrogen bonds form between water molecules, causing them to stick together. These same hydrogen bonds form between water and other molecules that carry charges. Here's an example of how water acts as an efficient solvent of table salt or sodium chloride. Water molecules surround the sodium and chloride ions of salt. The oxygen atom in each water molecule, with its partial negative charge, bonds to a positively charged sodium ion. The hydrogen atoms of the water molecule, with their partial positive charges, bond to the negatively charged chloride ions. Water's polarity makes it an effective solvent for charged or polar solutes. The hydrogen bonds that form between water molecules are responsible for one of water's most unusual properties. Although solids are usually denser than liquids, water expands and becomes less dense as it changes from a liquid to a solid. This property allows ice to float on water. Let's examine why ice floats on water. In ice, each water molecule forms 4 hydrogen bonds with 4 adjacent water molecules, giving the ice an ordered lattice structure. In this structure, the hydrogen bonds overcome the motion of the individual water molecules, holding them in a fixed 3-dimensional pattern. In addition, the water molecules are spaced farther apart, making ice less dense than water. As ice melts, hydrogen bonds are broken, and the water molecules are free to move closer together, forming liquid water. Liquid water, therefore, is more compact or denser than ice. What would be the implications for life if ice were denser than liquid water? The hydrogen bonds between water molecules are also responsible for another unusual property of water. A great deal of heat energy is required to change water's phase or state from solid, ice, to liquid, or from liquid to gas, steam. Water has an extraordinarily high specific heat or capacity to absorb energy. Specific heat is measured as the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Water's specific heat is unusually high because it contains many hydrogen bonds. A large amount of energy is needed to break the hydrogen bonds between the molecules before heat is transferred. Although liquid water is denser than ice, the molecules in liquid water move more freely. Entropy, which is a measure of the disorder of a system, is higher in liquid water than in ice. Notice that liquid water continues to absorb energy before it becomes water vapor. When liquid water has absorbed enough energy to break all of the hydrogen bonds, it changes from a liquid to a gas, steam. Water vapor has the highest entropy of the 3 phases. What does the graph tell you about the relationship between entropy and temperature?
So I just want to point out that this animation was from sumanazink.com and really does a nice job of describing both the polarity of water and how those molecules interact with each other to give water some of its properties. Some of those emergent properties of water include its cohesive behavior, which we'll look at in just a second, its ability to moderate temperature, which the previous animation showed you, its expansion upon freezing, meaning it becomes less dense as a solid than as a liquid, and its versatility as a solvent. So let's focus for a few minutes on cohesion. Cohesion is the attraction of water molecules to each other due to hydrogen bonding. This allows water to travel up the vessels in plants against the pull of gravity. Again, let me take a moment and show you this activity from pearsoncmg.com.
How does water get from the roots of a tree to its leaves? The evaporation of water from leaves moves water molecules up from the roots. The evaporation exerts a pull that is relayed downward along a string of water molecules from leaf to root.
So here you can see water is evaporating from the surface of the leaf. It actually starts up here to get the water to come out from the soil and go into the roots. And without that attraction, without those water molecules sticking together, that wouldn't occur.
Hydrogen bonds cause water molecules to stick together, a phenomenon called cohesion. As each water molecule evaporates, it pulls on the next water molecule, and it pulls on the next. This relays the pull of evaporating water molecules all the way down to the roots. The cohesion of water helps to keep gravity from pulling the water molecules back down.
So it's a pretty impressive property of water. Adhesion is how water molecules stick to other things, such as if you see a droplet of water right before it drips off the sink. That water connection between the water molecule or the water droplet and the faucet is adhesion. Adhesion is also part of how water molecules travel up from the roots to the leaves in plants. Another property of water is its moderation of temperature. We learned that water has a high specific heat. That means it can absorb or release a large amount of heat to and from the air with only a slight change in its own temperature. This keeps the Earth from drastic temperature changes and gives us fairly mild seasons, even though it seems like there's a big difference between summer and winter. On other planets, that difference is hugely more different than it is here, which allows living organisms to adapt between seasons. Remember that temperature is a measure of the average kinetic energy of molecules, so the average motion of the molecules gives us the temperature. Water also has a high heat of vaporization. This allows for cooling through evaporation. Evaporative cooling of water helps stabilize temperatures in organisms and bodies of water. We know that ice floats because it's less dense than water. This makes aquatic life possible in winter. Think about the pond. We know that the surface of the pond freezes, but The whole pond doesn't generally freeze solid, therefore living things can survive underneath the frozen water through the winter and come back in the spring. Water is also an extremely good solvent. That means lots of substances dissolve in water. An aqueous solution is a solvent, like water, dissolves a solute, like salt or sugar. Water is a versatile solvent because of that polarity that we mentioned before, that connection, that hydrogen bond between the hydrogen and the oxygen atoms. This allows chemical reactions to occur in living things, which we'll be talking about later this year when we talk about cellular respiration and photosynthesis. When an ionic compound is dissolved in water, each ion is surrounded by a sphere of water molecules, kind of like a hydration shell. We saw this in the animation just a few minutes ago. Water can also dissolve compounds made of non-ionic polar molecules. Even large polar molecules, such as proteins, can dissolve in water if they have ionic and polar regions. Two other terms that you need to be familiar with when you talk about water are hydrophilic and hydrophobic substances. A hydrophilic substance is one that loves water. It's attracted to water. A hydrophobic substance is one that does not love water. As you can see in the picture here, oil, which you know, floats on water. Therefore, it's hydrophobic. It doesn't mix in with the water and become equally mixed like something like salt or sugar would. This is important because cell membranes, which again, all living organisms are made of cells. Every cell has a cell membrane. Cell membranes are made of both a hydrophilic part and a hydrophobic part, which allows that membrane to interact with water and other things. For the last few slides of this presentation, I want to focus on pH. The effects of changes in pH are related to water. Concentration of hydrogen and OH minus are equal in pure water. So we have the H and the OH, and those are in equal numbers. Adding certain solutes, called acids and bases, modifies the concentrations of H and OH. Biologists use something called the pH scale to describe how acidic or basic a solution is. An acid increases the hydrogen ion concentration of a solution. A base reduces that concentration in a solution. The pH of a solution is determined by the relative concentration of hydrogen ions. Acidic pH is anything greater than 7, and a basic pH is acidic pH is anything less than 7, and a basic pH is greater than 7. Most biological fluids, the things that you find in your body, have pH values in the range of 6 to 8, so they're mostly neutral. If we take a look at this scale here, you can see battery acid is an extreme acid. Digestive, stomach juices, also a pretty extreme acid. Slightly less acidic would be things like vinegar, beer, wine, soda, and then so on down the scale. When we get to the other side, oven cleaner and household bleach are extremely basic substances. The internal pH of most living cells has to remain close to the pH of 7, which is neutral. Buffers are substances that minimize changes in concentrations of H and OH in a solution. Most buffers consist of an acid-base pair that reversibly combines with hydrogen. This relates to the world as we know it because there is this thing called acid precipitation. Acid precipitation refers to rain, snow, or fog with a pH lower than 5.6. Acid precipitation is caused mainly by the mixing of different pollutants with water in the air, and it can damage life in lakes and streams. When you think about something that lives in a stream or a lake, fish, macroinvertebrates, these are really sensitive. Most things are really sensitive to differences in pH levels. So if the pH level just is slightly off from what it should be, those organisms will die off. The effects of acid precipitation on soil chemistry are contributing to the decline of some forests. So just like things in water are sensitive to changes in pH, so are things on land, especially things like plants that derive their water straight from the soil. If you have any questions about the properties of water, feel free to send me a message.